proximate, or in Ed's case, distant, that is Ed Wilson in Geneva. I wish you all a happy new year. Tonight, our speaker is Dave Eagle, who will talk about observing and imaging our nearest star and the equipment and techniques to use to observe and image the sun safely. Dave is an amateur astronomer, planetarium operator, presenter, author, and tutor who's been interested in astronomy and looking up with wonder at the sky ever since he can remember, and who absolutely loves getting people enthusiastic about the night sky. As a very young boy, he used to gaze up at the night sky and wonder how it all fitted together. That puzzle started to unravel properly when he was 9 and discovered the plough for himself. Starting with some old 10 by 50 binoculars, he graduated to a small refractor bought by his parents for Christmas and learnt a lot from a kindred spirits in Southwest Herts Astronomical Society and Hampstead Scientific Society, until as a teenager, his attention was directed elsewhere, as it so often is, until his interest in astronomy was rekindled in 1985, when, as a newly married man with a daughter on the way, Halley's Comet returned and he bought his first serious telescope, a 3-inch refractor. In 1987, Dave established the Bedford Astronomical Society and is now also a member of Northampton Natural History Society. He was editor of the Handbook of the Federation of Astronomical Societies for a number of years and was elected a Fellow of the Royal Astronomical Society in 1996. He has been the lead astronomer for Hale-Bopp and Aurora flights for members of the public and is a STEMnet ambassador. He has a degree in biology and trained as a science teacher, but is now semi-retired and building on his interests in astronomy, wildlife, and photography. As I said before, he's a STEMnet ambassador and an astronomy and astrophotography tutor for adult education for Northamptonshire Council and runs their adult education astronomy courses. He's written articles for many of the British astronomical publications and supplied images to illustrate astronomy articles for photographic magazines, most recently 2 articles on astrophotography for Sky at Night. He also organised a number of successful astronomy workshops and hosted an evening to celebrate Tim Peake's Principia mission to the ISS. In 2013, his first authored astronomy book was published by Springer. With his wife, he enjoys travelling, particularly to places which are a naturalist's and photographer's paradise. David, the floor is yours.
Thank you very much. Hope my talk goes on as long as the introduction. But it's good to see you've read my website, which is great. Thank you very much for a great introduction. And thank you very much for inviting me along to talk to you this evening. Hope you all had a good Christmas and have a great 2023. Let's hope things start to get back to some sort of normality now, with a better pace than it has over the past couple of years. You mentioned about getting people enthusiastic about the night sky, but of course with the sun, it's also the daytime sky that I like getting people interested in the sun as well. And this all started, I suppose, about 8 or 9 years ago when I got my first dedicated solar scope. And I thought, well, it will give me something to do during the summer. Little did I know that the sun was going to completely entrance me and send me down a rabbit warren that, yeah, it's very difficult to get out of. And, of course, cost you lots of money as well. So I'm going to talk about observing and imaging our nearest star. And of course, as soon as we start to talk about the sun, we really have to firstly say you've always got to use extreme caution when you're observing the sun. You've got to make sure you're using, not going to work, you're using the proper equipment. So make sure that you're kitted out correctly to be able to do the observing that you want, to make sure you filter out all the dangerous radiation, etc., etc. So I'm going to do a quick introduction all about the sun, what it is. Of course, it's a star. Most of us know that, or hope we do anyway. And there you can see the size of it compared to the other planets, and you can see just how small the Earth is compared to the sun. Mainly made of hydrogen gas, and of course it's burning by nuclear fusion and turning hydrogen into helium. At the moment, of course, it's only halfway through its life, so it's still got lots of hydrogen left to carry on that nuclear fusion in the core. And of course, the star isn't particularly a particular big star. It's not particularly a very bright or hot star. And as you can see, it's a G star here, around about 5,000 to 6,000 degrees on the surface, which gives it that distinct colour. It's mainly white light it sends us though, so it's not as orange as most people would lead you to believe. But of course, when I do my images, I always make them orange because that's what people expect, a sort of tangerine colour, so to speak. But of course, different stars have different temperatures, so the really hot ones are white or blue, and the cooler ones, like Betelgeuse, are much redder. But our sun is a G-type star, so the surface temperature is between 5,000 and 6,000 degrees on the surface. Of course, it's much, much hotter in the middle where everything's going on. And there's also other stars that aren't listed here as well, but I'm not going to go into much detail about those. And of course, we've got the Hertzsprung-Russell diagram, which tells you all about the stars. So if we take the sun as being one solar mass and a temperature of around 5,500 to 6,000 degrees, that's where it sits on the Hertzsprung-Russell diagram. So on the main sequence here, and it's about halfway through its life, but it is going to develop and eventually it will change, but that's going to take a few billion years, so there's not anything for us to worry about at the moment. And here's an average star like the sun. It will go into a red giant and then a planetary nebula, and then eventually shrink to a white dwarf. And of course, long before it becomes a red giant, the Earth will get a lot hotter than it is at the moment, and it would just evaporate all the water off the Earth, and it will become dry, and we'll be gone. So we'd either have to find somewhere else to go, or yeah. And here you can see the life cycle of the sun. So there it is now. So you can see things are going to stay more or less the same for the next 4 billion years or so, and then it's going to start getting warmer where the Earth is and become a red giant, and eventually a planetary nebula, and then a white dwarf. Okay, so some facts about the sun. It's 99.86% of the solar system's mass. 1 million Earths could fit inside it. So it's 4.6 billion years old, because that's when our solar system was formed. It shines in mainly white light, and the surface temperature 5,500 degrees C. And it's about 333,000 Earth masses. The surface is made of plasma, so this is a highly charged gas, and electrons are roaming free about it. So if you could sap a battery and put it either side of the sun, it would conduct electricity, because those electrons are roaming free. And the way it works, it starts with a hydrogen atom with a proton and an electron there, and that's normally going around the electron in an orbit or a shell. Oh, okay, that's simplified, those chemists out there. Yes, but that's what we learn in lower schools before we go on to do degrees about shells and energy and electrons and things, and it gets slightly more complicated. So, but the hydrogen plasma, you've got the proton there and the electron, and that's just buzzing about wherever it likes, and it's all going around the sun, which gives it this charged energy. And 99% of all matter in our universe is in this plasma state. That's quite interesting. So, facts about the sun. There it is. So that's roughly the size of the sun to the Earth, and you can see this lovely loop prominence here in this particular image. You can see there. And the way it works with nuclear fusion, you get two hydrogen atoms and they get forced very close together due to the gravitational force of the sun, and then they fuse together to form a hydrogen molecule, H2, and produces a neutrino and a positron. And then once that happens, you then get a hydrogen atom and this hydrogen molecule, which come together and they form a gamma ray and a positron and a helium-3 atom. So that's how it all happens, and that energy is produced. And then we can react those two together, and that forms helium. Hydrogen produces a hydrogen atom and a hydrogen atom, and energy and light. So here's the sun's disk, and there's two ways of looking at the sun. The first one is the photosphere, which is one we know and love, which is the light sphere. So this is looking in white light. And when you're looking at the sun, you can see sunspots on there. You can see it's slightly dark around the edge because we're not looking at a solid surface. Remember, it's made up of plasma. This is highly charged gas. So when you look at the edges, you're looking deeper into that gas, and so it's a little bit darker. So you see these sunspots quite nicely, or active regions as they're also known. The darkening towards the limb, and there's also faculae as well, which is slightly brighter areas than they're usually best seen in that darker area towards the edge of the limb, and they're particularly prominent if there's a sunspot close to the edge of the limb. And then occasionally, if you're lucky and you're observing at the right time, you might see a solar flare associated with one of those sunspots, but they are fairly rare and they don't last for very long. If you're looking at different wavelengths in narrowband, in hydrogen alpha, we're looking at the chromosphere, which is a layer of gas a little bit higher above the photosphere that we can see. And this is known as the chromosphere or color sphere. So again, we still see this darkening towards the limb because we're still looking at a plasma. We can see the sunspots again, but they look totally different. You can see the magnetic fields around them, and I'll go into a little bit more detail about that in a moment. And we can also see these prominences sticking out of the edge, these huge loops of plasma following these magnetic lines, and these spicules, which are very short spikes just sticking above the surface of the chromosphere. And then filaments as well, which are these dark areas against the sun, but they are exactly the same as prominences. They are just prominences that are in front of the sun rather than on the edge. Because they're darker than the chromosphere, they look dark when they're superimposed in front of the disk. And of course, the sun is constantly changing. And when NASA point their instruments at the sun, this is the sort of thing they will see it doing. So here's a very active sunspot down here, and you can see it suddenly explodes, sending all this material out, and then you can see it splashing back into the surface. If only we could see it in that sort of detail with our amateur instruments. So here's a cross section of the sun. So you can see is the core, and that's where most of the nuclear fusion is going on. And then that radiation and heat and light comes out and takes probably millions of years to get to the top. And then you've got a convection zone here before you get to the photosphere, and then the chromosphere on top of that as well. Of course, the surface of the I've forgotten the name of it now, of the sun, the photosphere, is covered in these little granules, or this solar granulation. And that's caused by these convection currents that are going around a bit. If you boil a thick soup on the stove, you will see the same sort of thing happen as these convection currents come to the surface. So you get these granules formed on the surface of the sun. It can be quite a challenge, but using filters you can make that a little bit more prominent in your images and it's constantly changing as well. So if you have a look at this animation, you can see that granulation is constantly changing as those convection currents are changing and reaching the surface. So the most distinct thing we see on the sun are these sunspots, or active regions. And the sun goes through an 11-year cycle, and of course we're just coming out of the minimum, so the sunspot activity is starting to increase. And here's what a typical sunspot looks like. You can see this very dark area in the middle, a bit like a shadow. It's also known as an umbra, which is the darker part of the sunspot. And then the outer, no surprises, that's known as the penumbra, which is always a little bit not quite as dark as the central area of the sunspot. And you see the solar granulation around the sunspot as well. And these are caused by magnetic fields coming out through the surface of the photosphere. And again, they're constantly changing. So if you have a look at this animation, you can see the granulation here changing, but the sunspot itself is changing as that plasma is moving around in that magnetic field. And so we can identify which sunspot we're looking at. The sunspots are numbered, and they're numbered by the National Oceanic Atmospheric Administration, NOAA. And the sunspot numbering started in 1972. And in June 2002, they reached 10,000 sunspots. And so once 10,000 is reached, 9999 is the highest number sunspot, and so as soon as they reach 10,000, that goes back to 1. So back in June 2002, sunspot started at number 1 again. I can't remember what we're currently on. It's something like about 2000 and something, if I can remember rightly. So it's a little while since I did some solar imaging last year. And of course, depending on where the Earth is in its orbit, the path that the sunspots make across the sun as the sun rotates changes throughout the year. In June, they almost go straight across the disk because the angle of rotation of the sun is almost perpendicular to the Earth's orbit. But other times of the year, you can see they make a slight curve. Oh, in December as well, it's a straight line. So you can see that's at the equinoxes, or at the solstice, it's straight across the disk, and at the equinox, it's more of a curve because the pole of the sun is tilted a little bit more away from the Earth, either the north or the south, depending if it's March or September. But the sun doesn't rotate as a solid body because it is a plasma. And so you can see that as seen from Earth, at the equator, it goes around in 25 days, but at the pole, even though it's got less distance to go, it takes 35 days, so it's a lot slower. So you can see the sunspots, if there's different sunspots at different levels, they will pass one another in certain areas. But they don't all develop in the same place or all over the place. What happens is you've got the north magnetic pole, the south magnetic pole, and you've got the field lines. So as the sun rotates, because different parts of it rotate at different speeds, what happens is those magnetic field lines start to become twisted. So you can see those lines have changed. And then as they get wound up tighter and tighter, a bit like an elastic band, and eventually something snaps. And that's when you get maximum solar activity and maximum sunspot production. And you can see here these loops of magnetic field coming out of those magnetic lines, and that's when sunspots start to form. And you get a north and a south sunspot. So you normally get them in pairs, as you can see here. So as these loops of magnetic field lines come out of the sun, because the magnetic field is all twisted, you get a spot forming at the north and south pole of that magnetic field line. And of course, the sunspots are slightly cooler areas on the sun. They're not that much cooler, but because they are slightly cooler than the rest of the sun, they do look darker. So what does that look like? So here's a picture I took a while ago of a pair of sunspots in white light, and you can see that quite nicely, the two sunspots groups here, and you can see the umbra and the penumbra on both of those, and you see quite a bit of structure in there as well. I said that the sunspots change, so this is it near solar maximum in March 2001, but in mid-January 2005 you can see there's very few sunspots visible, and of course over the past few years we've gone through a very quiet period of sunspots. Haven't had that many, but over the last 2 or 3 years sunspots have started to increase as maximum solar activity picks up, because those magnetic field lines are getting wound up once again. So we've got an 11-year sunspot cycle, and you can see this plotted here where people have kept counts of the number of sunspots over the years, and you can see that the last couple of maximum 2010 to 2020 was a bit lower than some of the other ones. So I think there's a lot of people trying to wonder what's going on with the sun here. Is the sun a little bit more variable than we think it is? And that could be emphasized by looking back a little bit further to 400 years of sunspot observations. And if we look down here between 1600 and 1750, although they didn't do observations in the same way, there did seem to be a lot less sunspots around that time, what they called the Maunder minimum. And sunspots go through a routine of where they're being formed. So at solar minimum, most of the sunspots are towards the northern part of the sun, well away from the equator. But at solar maximum, most of the sunspots are found a bit closer to the equator. So you can see what's happening here. They're starting at the away from the equator, and then as the cycle progresses, they migrate more to the equator, and then back at solar minimum again, they migrate back out. So you can see there's a frequency here and the way the magnetic field forms these sunspots. And if you plot that, it gives you this distinctive butterfly diagram. So you see the sunspots at the start of the cycle were formed nearer towards the poles, and then as the cycle progresses, you can see they migrate further down towards the equator here. And you see that quite nice. And that's in both the north and the southern part of the sun. And of course, not all sunspots are the same. So us as humans like to classify things. So there is what we call the Zurich classification of sunspots. And you can see them here. So the A, B, C, D to J. And you can see that the different types of sunspots we get can be classified. I'm not an expert in this. I just like looking at the sun and taking pretty pictures. So I don't really do anything scientific with my images. But of course, sunspots can be very active and very exciting in themselves. Back in 1859, Richard Carrington was observing a sunspot with his telescope, and he noticed these two very bright areas here appear. And this produced the Carrington Event, and this was a huge solar flare that went off almost directly towards the Earth. So the Earth got the full impact of that particular outburst from the sun. Now, how that happened? Well, these twisted magnetic fields come out through the surface. They get twisted up even more, and then all of a sudden it snaps, and then this sudden rush of material is sent out away from the sun. So you can see here this solar flare. You can see nothing here at all, and then you can see it suddenly brightens to produce this flare. And this animation shows it quite nicely, and you can see just how quickly that goes off, saturates the instrument, and sends all this material. And you can see in the satellite there, all that graininess is associated with the active material that's being sent towards it. And of course, the atmosphere around the sun, the corona, is highly active, and there is a satellite called SOHO that's out there looking at it. The sun is about this size, and you can see when something goes off, you can see the corona does respond to that quite drastically when that material is sent out. And of course, not only does this give us great views of the atmosphere of the sun, it also shows us sun-grazing comets coming in and going out the other side. And those of us who remember Comet Ison a few years ago will remember that one coming in and then suddenly disintegrating and not coming out the other side. Again, the sun is about the size of that little circle in the middle there, so it gives you some sort of scale as to how big that corona is around the sun. Of course, one of the things to observe with the sun is eclipses. And of course, the best type of eclipse is the moon between the sun and the earth, which gives us a solar eclipse. And then the other one is the earth between the sun and the moon, which gives us a lunar eclipse. And then the third one would be the sun between the earth and the moon, but of course that will be apocalypse. So we're hoping that one doesn't occur anytime soon. And of course, if you can get to see an eclipse of the sun, that is an amazing view, because you see this corona in all its glory. I was lucky enough to be able to go to America in 2017 and see and image this eclipse. That's one of my images up there. But the strange thing is, although the surface of the sun is only 6.5 or 5,500 degrees C, the corona of the sun can be up to 3.5 million degrees C. So it's much hotter than the rest of the sun, which seems a bit strange really, but if you think about it, the atmosphere, the corona of the sun, is much more tenuous than the sun itself. So what's the best way to observe the sun? Well, the best way is to use a filter to look at it so that all the heat and light is taken out before it reaches your eyes. And of course, the simplest way and the cheapest way of doing it is solar glasses. Just put them on and they filter out the heat and light so you can see and get a naked eye view. Of course, you're only going to see eclipses of the sun when there's quite a big chunk taken out, and you're only really going to see the biggest of the sunspots when they're on there. You won't be able to see some of the smaller ones. You can use a pinhole projection, so if you've got a bit of a card and put a hole in it and you have the sunlight coming through, you can get the image of the sun formed on there. But again, it can be quite small. If you bring the card a little bit further away, you will get a bigger image, but it will get fainter. Some people have been quite inventive in using something like a colander to take images of an eclipsed sun, but I think you might strain your eyes looking through that one, so I wouldn't recommend it. Another way of looking at the sun is to use binocular projection, and this is an image I got off the internet to show you how to do that, but they forgot to show you that you need to cover one of the lenses, because you're going to get two images on the paper and they're not going to be matching, so you need to make sure you cover one of the lenses to make sure that you don't set fire to anything. These solar scopes are quite nice, and they can be used quite nicely to there's a mirror down the back here, so the light comes in through here, is focused onto the mirror and then reflected back onto here where you see an image of the sun. So if you're showing lots of people the sun, that's going to be one of the safest ways of doing that. The other way a lot of people do it is to use a telescope. So if you put a shade here to produce a nice shadow behind it and then project it onto a piece of card, you can produce a very nice image of the sun, and it's a lot bigger than just using a pinhole projection. But don't forget to cover the finder. If you're using the finder, make sure you cover that up to make sure you don't set yourself alight, or worse still, finders are normally made of plastic, so if that heat and light gets inside, it will probably melt something inside the finder as well, so quite dangerous. And it's quite an effective way of imaging the sun, and here's some images that I took quite a while ago showing an old Vixen refractor I had a while ago projecting the image of the sun, and this is just an image taken of the sun just by photographing the image projected onto the card. And here's another one as well. So you can see it's quite an effective method of imaging the sun. Fairly safe as long as you don't get your eye close to the eyepiece, because you are letting all that heat and light in through the telescope, so it will be quite hot. So make sure nobody puts their eye close to there. The other way is to use solar filters, which block 99.9% of all the heat and light coming in before it gets into the telescope. So that is much the safest way of doing things. You can get Barda film, there are other makes available. You can cut it to size and stick it to the front of the scope, but watch out, because there are two types. There's a visual one suitable for visual use and one for photographic. The photographic film lets through more light than the visual one, so it's not suitable for visual use. So make sure you get the right type for the use you want it for. Okay, so it cannot be used visually. Okay, so make sure you get the right type of film to do that. And then once you've cut it to size, make sure it's securely fastened onto the end of the scope so that a gust of wind can't blow it off while you're observing. So that's highly important. You can get pre-made solar filters like this. They're usually made to size, so they go right on the end of the scope for a particular aperture. They're usually a Barda film or similar sort of thing. And again, just like the homemade film, make sure that that is securely fastened on the end of the scope. I usually use a bit of black insulation tape to make sure that it can't come off while it's being used. And if you can't fix it with duct tape, then you're not using enough. Okay, so yeah, make sure it's secure. And then just as you're about to use it, just hold it up to the sun and move it around just to check that no light is coming through that filter. So you just see the image of the sun through the filter and not any chinks of light coming through, and that will ensure that it is suitable for use and you haven't got any pinholes that might let too much UV or IR light through there. And if in doubt, don't use it. Okay, going up in cost a little bit more for white light viewing is the Herschel wedge. This is the one that I use. It diverts 95% of all the heat and light away from the eyepiece. So this little disc here does get quite hot because that's where all the heat and light is going. It's a safe way of doing it, but it's after it gets into the telescope. So you need to use this on a good refractor that's not going to melt. So no plastic refractors. So all the heat and light reaches the Herschel wedge after it gets into the telescope. And the way it works, it has a wedge of glass in there. It's about 10 degrees. And the light comes in. So 90% of it is transmitted out the other side, and that's where all the heat comes into that little disc. You get about 5% is absorbed into the glass, and then about 5% is reflected to the eyepiece. So the solar image can still be quite bright and with a lot of glare. So subtle features, although you can see sunspots, subtle features are often washed out when you're looking at that. So filters can be used to help increase the contrast. So you can either use a neutral density filter or a polarizing filter. And I find a polarizing filter is better because you just need a single polarizing filter in your eyepiece. And if you screw it into the eyepiece and put it into the Herschel wedge, because the light coming off the Herschel wedge is partly polarized, you can just rotate the eyepiece to adjust the brightness of the image. And that's a great thing to do because you're making the image of the sun a little bit darker, you can then start to see some of the more subtle detail on the surface. The other one is the Barda Continuum filter. Now this gives a very strange color because it transmits 540 nanometers wavelength, which enhances sunspot and solar granulation detail. but it does make the sun look green if you're using it visually. I use it with my mono camera and it gives me absolutely great results. So yeah, I would recommend one of those if you're going to do imaging especially. So if you use it visually, it does give this green colour, so it does look a bit strange. So how does the sun's disk look in white light? Well, here it is. That's an image taken back in 2015, just a single sunspot on that particular day. So yeah, as you can see, the darkening towards the limb, faculae, there aren't really many visible, although there's a slight hint over here, and occasionally solar flares. And the surface you're looking at in the photosphere is about 300 miles thick. But if we look at it in a bit more detail, here's an image I took of a sunspot a while ago, and you can see the sunspot really nicely. You can see the umbra and the penumbra, and you can see this white brighter areas around it, which is the faculae. So you can see that quite nicely, and it stands out really well against the darker limb of the sun. If you want to move up a little bit in your observing and imaging, you can get a dedicated telescope or filter, and the Coronado is probably still the best introductory telescope for that, or a Lunt similar to this, dedicated, and you're looking at around about £800 to £900 for the PST, but for something like the Lunt there, you're looking at over £2,000 really now. So I'll have to check these prices again, because they've probably gone up since then. So the PST is a great introduction. It will enable you to have a look, but they are really difficult to do imaging because they're not really designed for imaging. I think they do that on purpose to make you want to go for something a bit higher spec. But something like that Lunt there is great for imaging, but it's very expensive. Now, narrowband imaging, the PST and the dedicated scopes use narrowband imaging. And if we're looking at hydrogen alpha, it looks down the red end of the spectrum, about 656 nanometers. And you're looking about 1,500 kilometers above the photosphere. So these filter out 99.9% heat and light before it enters the scope, but only lets these specific wavelengths through to reach the eyepiece. And because it has a red coloration. It's a monochrome image, so using a monochrome camera is the best for it, and I'll show you why in a little while. There is other wavelengths we can do. I don't do this, I only use hydrogen alpha. There's a calcium 2 you can use as well. This is looking at 500 to 1,000 kilometers, so looking a bit deeper into the chromosphere towards the photosphere, and it's down the blue end of the spectrum up here. Again, filters out all that before it enters the scope, but only lets those wavelengths reach the eyepiece, and that's got a blue coloration. And again, it's a monochrome image because you're looking at a very narrow wavelength. And if you're like me and getting on a bit, good luck if you can see anything, because lots of people have problems seeing the image through the telescope. Put a camera in and you'll see it no problem, but try an imaging. Try viewing the image, then especially if you've got older eyes like myself, then you will have trouble seeing the image. But how do these narrowband image scopes work? Again, most of them take out the heat and light before they enter the scope, only let through to certain wavelengths to reach the eyepiece, and at the heart of the instrument is something called an etalon. Now this is quite a complicated instrument. It doesn't look it because it's just layers of glass, but they have to be very precise. So there's different layers of glass with certain gaps between them, and they are extremely difficult to make. So you can see a normal gap less than 0.005 inches. So you know, and that is the reason why some of these telescopes are really expensive, because they have to throw away a lot of etalons because they're not up to par. It's an interference filter, so as the light comes into the scope, it sets up an interference and eventually only a certain wavelength comes through, and you can adjust that with the Etalon as well. So narrowband viewing with the Etalon. So you need to tune it. So if you start, you may get just a blank disc like that, but as you start to tune it, then you might just about start to see features coming in. So it has to be tuned before you see the things you want to see. And they can be tilt or pressure tuning, or even heat these days with the latest quarks. So this one has got a tilt tuner, and this one has got a pressure tuner, which has got this thing at the side. So as you adjust it, it squeezes the Etalon so that it changes the wavelength that's transmitted through the telescope. So you get what you want to see. You can also add things onto the end of the scopes here, and you can add a double stack on top as well, which makes the wavelength even narrower, so you can see even greater detail in certain parts of the sun. That just sticks on the end of the scope here. I had a play with one with my old 60mm Lunt, and someone at Kelling had one, so I borrowed it for an hour or so and had a go, and it did make a big difference to the image, but it did produce two images, so I'm not quite sure what was going on there, but I've not had that much experience with them to say for sure. So it can produce a double image. That's what I found anyway, but it did give much more detail to what you could see through the scope. Now, solar scope filters that can fit on a normal telescope. So you can just use an ordinary refractor and you can fit these filters on the front. Okay, they filter out 99.9% heat of light before it enters the scope. So you see it just fits on the front there, and they only let through certain wavelengths, in this case hydrogen alpha, to reach the eyepiece or the camera. And the image has got a red coloration, as you would think. But the way I observe the sun and image the sun these days is using the Daystar quark, which is just like this one here. It's a much cheaper option. It's just over £1,000, but you can use it on any telescope. It's not a dedicated instrument then. So, you know, if you've got a short focal length telescope and you use the quark, you get much more of the sun in. Use a longer focal length, then you see the sunspots in greater detail. So exercise extreme caution, because you may need an energy rejection filter, because it filters out 99.9% heat and light after it enters the scope. So you do need to use a good quality refractor to use one of these. Now, energy rejection filters aren't cheap, but if you're using up to about 120mm refractor, you shouldn't need an energy rejection filter, but you can use a UV IR cut filter to stop that heat and light going into the quark. There have possibly been quality issues with the quark. I've had mine about 7 years now, and it's running really, really well. So, you know, if it does go wrong, then I'll have to think carefully about what I do about replacing it. Again, they only let hydrogen alpha or calcium wavelengths reach the eyepiece, and the image got a red or blue coloration depending on what version you use. So I love the hydrogen alpha because it just shows so much detail, and the prominences as well. So here's the Daystar quark. So it's got a Barlow lens built in, so when you use it on a refractor, the field of view you're going to get is much smaller than you would expect, and it has to have that Barlow in to produce that parallel rays of light coming through the Etalon to produce the image that it gets. So yeah, so it's 4 times Barlow is built in there, so it gives a higher magnification and of course a smaller field of view. So if you're using on a long focal length refractor, you will only see a very small part of the sun. And of course, the image is going to get fainter as well. But the thing with these quarks, because you're heating them up, they do take longer to tune. So it's got a little dial on it that you adjust to change the heat and change the wavelength. And every time you make a change to that, it can take up to 20 minutes for it to come back up to temperature and go green again. And then it tells you that it's where it is. But once you've found the sweet spot on your particular quark, you just leave it at the same setting every time you go out. Daystar have followed up on that with a dedicated solar scope. They've got smaller ones called the Solar Scout here, and the one I'd love to have a go at is the Quark Gemini, because it's got a chromosphere and a photosphere and a prominence version built into the same device, and just by sliding that arm backwards and forwards you can look at the differences between what the chromosphere version and the prominence version give you. I have the chromosphere version and I see lots of prominences, as you'll see as we go through some of the images I'll show you at the end. So here's what we're looking at. So in white light we're seeing the photosphere here, and you can see in hydrogen alpha the it's a area above the photosphere. So you're looking at different layers of the sun with those different instruments. So the photosphere and the chromosphere or color sphere. And that's about 30,000 miles above the photosphere in extent. So there you go. So there's a image taken with the quark, and you can see the prominences quite nicely. So this is with the chromosphere version. You can see the prominences really nicely, and you can see the details in the sunspots here as well. The darkening towards the limb as before, sunspots, prominences and spicules, and of course these dark filaments as well. And plagues as well, which are these bright areas around sunspots too. So sunspots, active regions, are darker, slightly cooler areas. Plagues are bright patches usually associated with sunspots that we see with the hydrogen alpha. Solar flares, which are rare, very active solar storms. I did a solar workshop a few years ago, and part of that was to go out and take some images of the sun. We went out and had a quick look, came in, and then about 10 minutes later a solar flare went off. So had we been out 10 minutes later, we'd have seen the solar flare go off. So that was quite a disappointment. But they are quite rare and they don't last very long either. So prominences are these clouds of plasma suspended above the sun in these magnetic fields. And the filaments are prominences seen against the sun's disk, and they look darker. And the spicules are the furry edge to the sun's limb. So sunspots, slightly cooler areas associated with magnetic fields. So here's a image of a sunspot group that I took a while ago. You can see the solar granulation here as well using the filter. And here's the same sunspot group taken in hydrogen alpha, and you see the magnetic field lines of the plasma snaking between the two sunspots. And here's a nice couple of images showing these plagues around the sunspots as well. And here's a nice solar flare, not taken by me, I'm afraid, because they are very rare, but they are very active solar storms. And of course, were one like Carrington's to happen today, it would probably knock down most of our power systems and satellites. Yeah, it's something that people are quite aware of these days about it. Prominences show up quite nicely. This was one of the original images I took with my Lunt a while ago. So there's the clouds of plasma suspended above the sun in this magnetic field, and they can last for days on end. They can last, but they're continually changing. And there's another one as well, and they're all so different. There are many different types of prominences, ranging from hedro prominences, fans, got these really active ones which I'll show you in a minute, surge prominences, and loop prominences, which I'm still yet to see. I've still yet to see a loop prominence. I nearly got one when I was observing this one. You see over a number of times I saw this coming up and I thought, oh great, we're going to get a loop, and then all of a sudden it just went, decided to go back again. So I still haven't got my loop yet, but we'll get there. I'm sure we will. This was one just leading up to the eclipse in America, and you see it looked like a hand reaching out towards the moon to welcome it ready for the eclipse. So that was quite nice. And again, that was continually changing, and as you can see here, you can see it started to come up, form this hand, and then just collapsed in on itself. So yeah, it's continually changing, as you can see. If you've got the patience and you're taking lots of images, you can put them together into an animation, and I've done this quite a number of times with a number of prominences. And here you can see this prominence taken a few years ago. I think this is about 5 years ago now, and you can see how it changed over about 2 hours. So you can see this material is being suspended above the chromosphere surface by those magnetic fields. That was 2.5 hours capturing 60 seconds of video. 150 different videos were captured, and then of course to produce that animation, there's a whole day then spent processing and producing the animation. So if you're going to get into this, you need lots of time. Another one I was really excited to see, because it changed within 10 to 15 minutes, was a surge prom. And here's an animation I put together, and I colorized this one to show what was happening. You can see how it suddenly spurts up, it went back again, then all of a sudden it shot out again. And you can also see these spicules sticking out from the sun here, and you see this puff of material coming out here and moving along that magnetic field line away from the sun as well. And of course that was all as I was taking the video. You could see it changing, it was that active. So that's an animation taken over about 20 minutes. There's a white light version of a sunspot. So you can see the darker area along the limb, you can see the faculae, and you can see the sunspot showing a nice Wilson effect, which is this, it looks like a bowl effect. But if we look at the same sunspot in hydrogen alpha, you can see just how different that looks. It's a slightly different angle as well. So here's where the sunspot is, and you see just how differently that looks compared to that one. And here's another animation showing a really active sunspot, and you see how active that really is. I always get excited when a sunspot is approaching the limb, because you never know what sort of activity you're going to see as that approaches the limb, because that's when you see all this lovely activity going on. Oops, wrong way. So here's a prominence and here's a filament. It's exactly the same thing as I said, but this one is looks darker because it's silhouetted against a much brighter chromosphere of the sun. And here's a very long filament on the solar surface. So the prominence is seen against the sun's disk. And again, there's another nice active prominence and spicules, and another nice filament here. That furry edge is also known as the chromospheric network, apparently. So if you look in calcium wavelengths, this is what you get in white light, but this is what you'll get in calcium wavelengths. I'm not really into calcium, mainly because I can't see it anyway. Yeah, so that's what you get. You see the sunspots, you can see these bright areas similar to faculae around them. That's about it, really, with the calcium. So I did hear a comment that imaging the sun is very easy. Well, you know, we always complain about astronomers that we haven't got enough light, we haven't got enough data. Of course, the sun sends us too much light and heat, so we have to tame it, which is why we need to use the filters. Yeah. DSLR imaging is best suited to white light imaging. You can take images using a DSLR. So this is the Mercury transit. This is Mercury and this is a sunspot taken in 2016. And that's the sort of thing you get. But if you use a DSLR, this is the sort of image you will get if you're using a hydrogen alpha quark or dedicated solar scope. With a white light, it's fine. You can see some, images, but this is taken with a monochrome camera, and you see just how much detail you're getting. But this one is with a DSLR, and it's very difficult to get the detail because a one-shot color camera like a DSLR has got this Bayer matrix built into it, so the blue and the green pixels will not detect any of the light because it's only that red part of the spectrum that comes through on the red filter. And of course, that's only a quarter of the imaging chip. Webcam imaging, color webcams best suited for white light imaging, but because they're less sensitive to hydrogen alpha and calcium wavelengths. But monochrome webcams, I use monochrome for both my white light and hydrogen alpha imaging with my telescope. And then of course, you've seen the color, they're all taken with monochrome cameras, and I just add the color later. And of course, depending on the chip size that you're using, this was one of the old cameras I used to use, a DMK41 with a 60mm lens, and you can see the sort of scale you used to get. But with the DMK21, you can see it's a smaller chip, so therefore you got more of the less of the sun in view when you were doing that. So taking your images, you get the image scale you need. Yep, you could eyepiece, depending on what you do, and then you replace that with the camera. Or you could use a camera and a Barlow lens. If you put a Barlow lens in and then put your camera in, you can get a smaller part of the sun. And then if you then add a spacer in between the camera and the Barlow, you can then get an even smaller view, or even closer view of the sun. But don't forget, every time you magnify the image, you're spreading the light out, the image gets darker, so you need a longer exposure, so it's not quite as good as freezing the seeing for the images. And then of course, getting your exposure right is a nightmare. So here's a short exposure, and you can see the chromosphere quite nicely, and you can just about see the prominences. But if you expose it longer, you can see the prominences really nicely now, and this really shows just how faint they are compared to the rest of the chromosphere. And there is a way of combining those together, and if you've seen my solar imaging book that I had out a while ago, you can combine those two together to create a composite image to show both. But these days I just take a single image and then manipulate the image so it brings the prominences out. There's also the problems of a hotspot. So what you will find is the image has a hotspot. So you can see this is quite nice over here, but over here it's overexposed, and it can be quite difficult, especially if you've got a large chipped camera, getting rid of that really bright part of the image, because as you adjust the etalon, you might find it sort of rotates around the sun and you never really get rid of it. The other problem people find when they're imaging the sun is this problem with Newton's rings, and these are diffraction images caused by the camera, and the way to do that is to use an adapter to tilt the camera relative to the light path, and they're available from other places these days. This is the one I use, and you attach your camera on here and then attach that to your quark or your solar telescope, and it tilts the camera slightly and it gets rid of those rings really, really nicely. But you need the quark adapter if you're using the quark to attach it to your quark in place of the eyepiece adapter. Software required, I use SharpCap for most of my imaging, or you can use Firecapture or any of the other software that comes with the cameras. AutoStacker I've been using for processing the AVIs, but I've now just recently, after lots of playing around, I've started to use Astrosurface for a lot of my imaging these days. So when I go back to doing some solar imaging, I'll be trying Astrosurface to see if that gives me much better solar images than I've got before. And Registax I've been using to sharpen the images as well, but again, Astrosurface seems to do a much better job. So again, when I start to get new data for solar imaging, I'll be trying that out as well. And then image processing software, so something like Photoshop, or Affinity Photo is out now as well, and Google Nik Tools is quite useful if you've got the free version of that. The newer version they are charging you for now, which is a bit of a shame. So Photoshop or Affinity Photo are great. PaintShop Pro, Google Picasa, or the GIMP if you like a free software. But there's many others, and each of those has got its very steep learning curves in them. So using the correct software really can transform your images. As you've seen, it does take time to process those images, and especially with the sharpening process, try not to over process the images. But the other thing to think about is do them to your liking. They're your images, so do them how you like, and then publish them, get them out on social media, on your club society webpage, whatever. Just share them and show them off at your local club. But round up is always use extreme caution with the sun, and don't stay exposed to the sun for too long. Yeah, make sure any finder scope caps are on, because I was out imaging once and I put a blanket over my head and suddenly thought, what's that smell? And then realized that the blanket was starting to smoke and I'd left the finder cap off, and that was a ruined finder because it had melted the inside of the finder scope. So be careful, we can all get caught out. And view or image mid-morning or late afternoon. Best mid-morning, because before the sun gets too hot, once the sun gets hot and the temperature goes up, then we do get lots of atmospheric effects and lots of turbulence. So, you know, once the sun gets nice, reasonably high up in the sky, but not too hot, that's the best time to do it. And the best thing is, best advice is to just enjoy doing the hobby. Get out there and have a go. So I think I'm just finishing off now with some images. So, you know, just using the projection method. This was a Venus transit a good number of years ago, taken just using projection onto a card, and then here's taken through the telescope. My setup was a little bit more basic back then, 2004 that was. Yeah. The next Venus transit, 2117, so I don't think I'm going to make that one. And then the one after that is 2125, so because they always occur in pairs. Mercury transit 2016, I already showed this image there. And in hydrogen alpha, this was similar view shown in hydrogen alpha, and you can see that quite nicely. You can see the dot of Mercury here and just how big it looks compared to the sun, and some lovely filaments and sunspots around there as well. And then here's an image I took showing it a little bit closer as it progressed across the disk, and a little bit more detail there. And that was another Mercury transit. Was that 4 years ago now? Ooh, 3 years, just over 3 years ago. Crikey. But the next Mercury transits, we don't have to wait quite as long. 2032 and 2039, both in November. So sun's going to be a little bit low, but you know, it's great. But of course, the ultimate experience of observing the sun is, of course, a solar eclipse. And if you've seen a partial eclipse and think that's an experience, a total solar eclipse is unbelievable. As that disk gets thinner and thinner, you really don't realize, once that disappears, what effect it has on your surroundings, your feelings, as that disappears. And then of course we start to see that outer corona appear. We can see these prominences. There were prominences on the edge of this, and the view through binoculars, because while the sun is in eclipse, you can view the eclipse in total safety with any telescope binoculars or anything, but you have to make sure you take them away before the eclipse finishes and the diamond ring appears. And the view of those beautiful pink prominences through the binoculars was absolutely amazing. Of course, the longer exposure you do, the more of that corona you're going to reveal, and then take a bit more care and you get these wonderful structure in the disk surrounding the atmosphere surrounding the sun. And you might just about be able to see a little bit of detail on the moon surface, but from light reflected onto the moon, but that required a much longer exposure, which I did try, and then realized I'd made a mistake in taking my images. You can just about see the moon's surface there, lit up by Earthshine, but because I'd left the filter on the end of the lens I was using at the time, it's created this horrible artifact in the image. So if I get a chance to see another eclipse of the sun, then I'll make sure that I take the filter off the end of the lens that I'm going to use. And then, of course, all too quickly, the solar eclipse was over far too soon, and yeah, it was all over. So if you want to know a bit more, then Lucy Green has got an absolutely fascinating book all about the sun, 15 Million Degrees, A Journey to the Centre of the Sun. And a great reading about the Carrington Event is by Stuart Clark on the Sun Kings. Hope you've enjoyed my talk. If you have, and you'd like me to come and do another Zoom talk, then I've got quite a number of talks. This one is going down well, virtually, Out of the Darkness, all about Pluto, New Horizons and Arakoth. Of course, it's a few years now since New Horizons explored Pluto. And of course, we're talking about the sun today, so why not get me back to talk about my experience of going down to view the eclipse in America in 2017. And then, of course, we're 4 decades on from the Voyagers being launched, so this talk is also going down well too. Okay, just to finish off, I'm going to promote my Sky Diary, and that's available completely free on my webpage, star-gazing.co.uk/diary. On there, you'll find 3 calendars. There's the blue one, which is any events that are going on in the sky that you can go out and observe. There's the red ones, which are events that I know are going on either physically or virtually that are open to members of the public. So I add them on as I find them available. And the black one is any notable space dates like anniversaries of spaceflight, etc. Completely free. It's on TeamUp. So what you can do is download the TeamUp app, put in the calendar, and you can carry it around with you, and it's updated automatically. I know 1 or 2 of you already friends with me on Facebook, so hi folks. You can also follow me on Twitter while it still lasts. It's still going, isn't it? Yes, it is. And all the images that I take, I put on Flickr, Eagle's Eye on the Sky. So have a look at me there. And then before I finish, I'll just promote my astrophotography guides. So I don't have one on solar imaging these days because the one I did have needs totally updating to reflect what I do now, but it is still available on Amazon if you have a look on there. But I also have guides on using Deep Sky Stacker to stack deep sky and comet images. Also one on Photoshop image processing for astrophotography. And of course, the new kid on the block for image processing is Affinity Photo, which compared to the cost you have to pay for Photoshop with a monthly subscription, this is a one-off cost, and they've just released this version 2 of the software. And I do all my image processing, not just astrophotography, but all my other wildlife, etc. imaging on there as well. And then just launched a couple of months ago is the high resolution lunar and planet imaging to give you a nice workflow to get the best out of taking moon and planet images. And of course, Jupiter and Saturn and Mars have been quite spectacular. If you go to my website, star-gazing.co.uk/shop, you can buy them all on there. And then just to finish, I thought I'd show you a time lapse I took of our experience seeing the eclipse from America. Yeah. Thank you very much.
David, thank you very much indeed. Rich in long-standing practical experience. That was a magnum opus. Martin, could you unshare your screen, please? Because then I can better see. Martin has raised his hand. If you mute yourself. Which Martin was it? Where is he? Martin, where is it? Martin is the question. Oh, he might have put it on chat. Martin, are you unmuted? Yeah. We have a clangor.
Technology, don't you love it?
Are there any questions anyway? Martin obviously had one, but while we wait for connectivity. Who is it? Oh, Martin, if you put yours in chat, I'll repeat it.
Young Mr. Axter, what the back there?
John.
Dave, thanks very much for the talk. I have the Affinity book you produced, but there's no upgrade from the version 1, which I bought, to version 2. Is version 2 worth buying now that I've got version 1?
To be honest, no. From an astrophotography point of view, it looks a little bit different. There are probably changes they've made in the background, I would guess. So it does look slightly different. The way it behaves is slightly different. But at the moment, for astrophotography, there are no extra astrophotography tools built into it. So at the moment, I wouldn't say it's worth upgrading, but for the fact it's what I'm not still sure if it's still on the bonus price. But if you think about it, for the cost it is, you know, within 3.5 months, it's cost you less than it would if you've had Photoshop. So, you know, for me, it's worth me upgrading, because obviously I like to keep ahead of the curve. Because I didn't use Affinity Photo for a good number of years, and someone recommended it to me probably 5 or 6 years ago. But it was only when people started coming onto my workshops and they didn't have Photoshop and said, how does this work? I don't know. So I had to learn it. And now, yeah. So, yeah. So from an astrophotography point of view, version 1 will do everything that you need to do. And there isn't anything in version 2 that would make you want to upgrade at the moment.
Thank you very much.
Okay.
Thanks.
Martin has posted.
Martin, do I normally worry about getting the sun the right way up? I do try to get it the right way up, but there again, it depends who you discuss it with, because there are some people who say that north should be at the top, and some people say that south should be at the top. So, you know, I always try and make it with north at the top, so it matches what I can see in either space weather or the hydrogen alpha stream images that are coming through. So I normally try and orientate my camera so it's similar to that. But if I'm imaging like a prominence that's really active, I will rotate the camera so it's taking less of the sun and more of the prominence that's sticking out, so the orientation of the camera matches what I'm trying to image. So quite often it won't be in the same orientation as it is in the sky, especially if I'm concentrating on one particular bit. But if I'm doing a full disc or a huge part of the disc, I normally try and get them about the same orientation. The movement. Yes, it's because we're looking at the sun from a slightly different angle. So if you imagine, my head is my head is the Earth, and my hand is the polar axis of the sun. So in midsummer and midwinter, it's straight on, and then it tilts backwards and forwards as we go around the sun. And so when it's tilted away from us, then the sunspot path will curve upwards, and when it's tilted towards us, the sunspot paths will curve downwards. Okay, so that's why we see those different paths of the sunspots as the sun rotates. It's just because from where we are in our orbit, because the orbit is slightly inclined to the sun's rotation, that we see those different paths, because of we're observing the sun at a different axis, tilt towards or away from us.
For the assembled multitude here, that was Rachel's question, which was, when you mentioned the path of the sunspots changing, e.g. straight around the solstices and curved paths of the equinoxes, is that their path is actually changing on the sun, or is it how they appear to us from our position?
Yeah, the sun rotates exactly the same. You know, they do go around in a straight line, but it's just our viewpoint of the sun changes due to its actual pointing towards or away from us.
Any other questions?
The Carrington Event obviously had a large solar flare associated with it, and the effect on the Earth was because it came directly to the Earth. Do we have solar flares on a regular basis that are of similar strength, but they don't point towards the Earth?
Yeah, we do. Not quite as big as that, but we have had quite active ones that have gone off, and it's sent it off in a direction away from us. So we have observed them, but because they're further around the limb and not directed towards the Earth, then most of that activity goes off away from Earth. So yeah, so there have been ones not quite as large, but there have been some quite big ones. And you know, as we go through the solar cycle, we might see quite a number of active sunspots. Could produce a solar flare. So but they normally flag those up, especially on space weather. If you look on space weather regularly, that will tell you about any sunspots that they think could be fairly active and perhaps could produce a solar flare.
Other questions?
The slide you've got of spectral classifications, you have the sun is a 5,000 to 6,000 Kelvin temperature, and then it says that the spectral features were metals and ionized metals, especially ionized calcium. And I just was like kind of going, well, how do you get that out of a helium and hydrogen star?
Let me go. I'm just going to go back to the slide. Hold on a sec. It's what we can detect in the sun. Because don't forget, our sun, although it's mainly hydrogen and helium, it's not a first generation star, so that it will have been seeded with a lot of products from supernova, from past supernova, because it's about a third generation star. So there will be quite a number of other elements in there, which is why we see calcium in there. You know, we've got the calcium light. So yeah, so we can see those in there. But it is mainly hydrogen and helium, but there are lots of other things in there because it is a third generation star, and there are lots of products produced in stars and supernova inside the constituents of the sun.
Any other questions? Well, thank you, Dave, again. Perhaps if we could all thank you in the traditional way. Right. Next month, our meeting will be on the 9th, that is the second Thursday, given by Chris Brockley-Batt, who works at MSSL. And she's actually going to tell us something about the physical processes. She's a mechanical engineer, first and foremost, about how you make equipment that is going to suffer the indignity of lots of vibrations on liftoff, and then the sorts of environment in which the satellite in which the equipment is put will survive. So I think that's going to be interesting and very practical. But as I said, that's unusually on the second Thursday of next month. It'll also be in this lecture theatre. And then, as you can see, we've got Martin Lewis on the principles of modern planetary imaging, Grant Kennedy on the life and death of a planetary system, Gavin Dutton on observational cosmology, and then Karen Aplin on the charge of the spheres, which is about extraterrestrial lightning and lightning that occurs on other solar system objects. Before you go for your biscuits.
Nick, once you've got that slide up, can you tell us which of those the speaker will be present and which ones the speaker will be on Zoom?
Chris will be present. Grant Kennedy, no, I beyond that I can't. Karen Aplin will certainly be on Zoom. She has health problems which will make it much easier for her to appear on Zoom. Before we take a break, two things. We did have a very successful pair of training days when we saw a total of 10, was it? I think people, John Evans, Martin and I, showing them the principles. Needless to say, it was a night, or both of them were days where it wasn't possible to go out and other than get wet. But we are hoping to have some practical sessions to ground what they learnt in practice as soon as it looks as if there's a reliable set of evenings. For anybody who missed that, and this will be those here or those either watching live or watching the recording, don't hesitate to get in touch with me, because it would be quite easy to have another session. We know that after 2 and a bit years, there are quite a lot of people who declared an interest in learning a bit how to use the equipment they've got, or what equipment they might like to get if they were going to buy a telescope. And I know I've had a number of queries in the last week asking the same question. Then outreach, we have a particular, during sometime in March, somebody at MSSL who helps run First Merrows Scouts, so not very far away from us, would desperately like to have a group of people go along and help their scouts towards their astronomy badge. Now, we've done this in the past. I'm quite happy to participate in that or lead that first thing. We'd still could usefully do with somebody to take and run with the Outlook. You don't have to do it all yourselves and so forth. But if I could find 3 volunteers who can email me, if you haven't already done so, and say, in March, I will give you a hand to do that. I'm particularly anxious to do this because the lady at MSSL is somebody who is influential in our ability to be there in the first place. Then another appeal for what volunteers. Remember, I sent an email before Christmas, but sometime in the autumn, saying that Rob Graham would quite like to hand the baton of doing WhatsApp to someone else because he feels he'd like a break, and he also says that he feels it's getting a bit stale. I don't think it is, but the lad's been doing it for a while. So we don't necessarily need only one person to do it. It could be done turn and turn about, or by a triumvirate, but presented by one of them each month. So please, if you feel that you would be able to do something akin to WhatsApp, it doesn't have to be exactly the same as Rob does it, then please get in contact with me as soon as possible. Rob's quite happy to do, I think, probably till the end of this session, but I would desperately like within a couple of months to find people who are willing to take up the cudgels. Right, there'll be a 15-minute break for biscuits and a walk and natural break.